Welcome to my presentation. My name is Koll. I'm from the Kepler University in Linz, Austria, and this work is being developed in cooperation with the steel producer voestalpine in Linz. At first, I want to give an introduction and motivation of my work. The superior objective is the precise estimation of thin electrically conductive coatings on ferromagnetic steel substrates using eddy current testing. And the coating thickness estimation accuracy depends on the signal, noise, and measurement. The used signal processing method, for example, Fourier transformation, the selected parameter estimator, for example, the least squares estimator, the number of excitation frequencies, the coil geometry and setup, and the material parameters. Here you can see the eddy current testing coil, which is used to detect the coating thickness of the steel sheet. The excitation coil is powered by a sinusoidal excitation current at different frequencies, and the induced voltage U is measured. Then, via fast Fourier transformation, the amplitudes and phases of the signals are estimated. Since there is noise on the signals, also the phase and amplitude estimation of the signals is associated with an uncertainty. Then you can display the results in the complex voltage plane, and you can apply a model-based estimation approach to get an estimate for the coating thickness C. And then, of course, also this coating thickness is associated with an uncertainty. And now the question arises, how does the whole measurement chain impact this uncertainty in the coating thickness estimation? And the goal of this paper is to develop a model which describes this uncertainty. In my work, I'm using a current coil consisting of three coils: one external excitation coil and two internal pickup coils. They are wound in opposite directions, and the induced voltage U is measured. There's an analytical model of this application, well known in literature, and it assumes linear and isotropic and homogeneous material behavior. The coating thickness is assumed to be diamagnetic, so the permeability mu1 is 1. Furthermore, the coating conductivity, the coating thickness C, the substrate permeability mu2, and the substrate conductivity sigma 2 are important parameters. As already mentioned, the noise in the measurement impacts the uncertainty in the coating thickness estimation. Therefore, an analytical noise model is necessary. In this context, the sinusoidal excitation current with additive white Gaussian noise is assumed. And then the amplitudes and phases are estimated via FFT, which leads to these formulations for the standard deviation of the amplitude estimation and the phase estimation, independence of the number of acquired samples and the noise. Since the analytical model is available in complex form, it's also a good idea to transfer this noise in the amplitude and in the phase estimation into real and imaginary part. Furthermore, it is assumed that the induced noise in the excitation current transfers into the secondary side measuring voltage, which is described by these relationships. On the left side, you can see a picture of measurements in comparison with the noise model. In orange, the current amplitude spectrum, and in blue, the voltage spectrum. And you can see the agreement is good. Now I come to the parameter estimation accuracy model. The Fisher information matrix is a key concept in statistical signal processing. It measures the sensitivity of the likelihood function to changes in the parameters of the model. In my work, I'm applying the Fisher information matrix to frequency discrete and complex data. Furthermore, it can be used to get a lower bound for the variance of an estimator. Therefore, a signal model is necessary, which is described by the deterministic eddy current model plus the additional stochastic noise model. This signal model is also separated into real and imaginary part. And then the Fisher information matrix can be calculated for all frequencies with the directional derivatives to the parameters to be estimated. Furthermore, the covariance matrix sigma is required, and the entries are described by the noise model. Furthermore, it is assumed that real and imaginary part noise are uncorrelated. And now, from the inverse of the Fisher information matrix, the variances of the parameters that J will be estimated can be determined from the main diagonal. On the left side, you can see the results for the normalized coating thickness estimation standard deviation for different parameter estimators. For example, if just the coating thickness C is estimated, then the normalized standard deviation is 1. If, for example, the coating thickness C and the lift-off between the sensor and the steel sheet is estimated, then the standard deviation is increasing. The interesting estimators are now 4 and 6. For example, if the coating thickness C, the lift-off L, the permeability mu2, and the coating conductivity are estimated, then the standard deviation rises significantly. That's going up to 3,500, and here to 5,000, which means the parameter, the coating thickness, is not estimable. On the right, you can see in comparison the directional derivatives to the different parameters displayed in the mutual impedance plane. You can see that the arrows for the coating thickness and for the coating conductivity always point in the same direction for all frequencies, which means that these two parameters cannot be determined independently of each other, which confirms the results derived by the Fisher information matrix model. To validate this, I need a measurement setup. A measurement PC is used to generate the signals and to do the signal processing afterwards. The connection to the hardware was made by a DOQ box with 1.25 megasamples per second. Then the signal is smooth and amplified by a linear power amplifier. Then the differential voltage of the eddy current flow is measured, and the shunt voltage is measured, filtered by anti-aliasing filters, and then recorded by the DOQ box, and then the mutual impedance is calculated for each frequency. In my work, I use excitation frequencies between 400 Hz and 200 kHz, and the excitation current amplitude is 0.2 amps. Here you can see a few pictures. Picture of the entire measurement setup. Here you can see the differential coil system existing of the outer excitation coil and the two measuring coils which are placed inside. Here you can see a sample. The sample is an electrical steel sheet M850A with a silver coating of a coating thickness of 21 micrometers. Then for the parameter estimation, I'm using a model-based least squares estimator over all frequencies. And so I can derive an estimate for the coating thickness C. All other parameter values are assumed to be known, and the substrate material is assumed to be linear, so the permeability is constant 900. At first, I analyzed the impact of the air gap on the coating thickness estimation variance. Therefore, I used 19 excitation frequencies between 400 Hz and 200 kHz, and different lift-offs between 5.85 millimeters and 58 millimeters. I did 100 measurements at each operating point, and then estimated the coating thickness, and then calculated the standard deviations. As you can see, in blue is the absolute coating thickness estimation variance over the lift-off. You can see with increasing lift-off, the coating thickness estimation standard deviation is increasing. This is the model one, and here is the measured one. You can see there is a gap between the model and the measurement results. And in red, in comparison, you can see the normalized results. And you can see the normalized model shows very good agreement with the theory. So therefore, that means that the model can be corrected by a multiplicative factor Kepler to improve the accuracy. Secondly, I analyzed how the selected frequencies influence the coating thickness estimation standard deviation. Therefore, I analyzed the frequency vectors from this table. For example, if a small excitation frequency of 463 Hz is used, then the coating thickness estimation standard deviation is very high. for example, if two frequencies are used, then the standard deviation is decreased.
Which one is it? Which one?
If you compare now frequency vector 4 with two high frequencies here,
The second.
with frequency vector 6, which consists of 19 excitation frequencies, you can see there's just a little bit of benefit if you use more excitation frequencies. In pink, you can see the absolute standard deviation again, where you can see a gap again between the model and the measurement results, and in black, the normalized results, which also shows very good agreement with the model. So the key takeaway to measure is that higher frequencies perform better, and there's just a minimal benefit when the number of frequencies is increased. Then I come to my conclusion and outlook. A model based on the Cramér-Rao Bound was developed to describe the model-based layer thickness estimation accuracy in eddy current testing of metallic coated electrical steel sheets. Then the model incorporates key factors such as noise, parameter settings, the number of excitation frequencies, and the Fourier transform-based signal processing. This new model now enables the development of a maximum likelihood estimator to improve the parameter estimation, and furthermore, this model can be used for an optimization of the signal processing method and the coil geometry to achieve a desired level of parameter estimation uncertainty. Acknowledgement, my literature, and thank you.